speaker is Sergei Morris from Technische Universität München, and he's going to tell us about Z2 gauge theory coupled to fermionic matter. Sergei, the floor is yours.
Thank you. Thank you very much. It's my great pleasure to tell you a bit about our recent work. Let me ask, could you see my cursor?
Yes. Yeah.
Yeah, this work was done together with my PhD student Umberto Borlo, a postdoc Bilahari Evanesan, and my colleague from TUM, Frank Polman. So let me start with, generally I'm interested in the interplay of gauge theories and fermions, and this often leads to interest in physics. So I summarize here some well-known examples, such as, for example, the half-field Landau level, phase diagram of quantum chromodynamics, condensed matter quantum spin liquids of Kitaev model on a honeycomb lattice. And so it's my belief that we can understand better the interplay of gauge theories and fermions by studying simple gauge theories with simple building blocks. So this motivated us to look into arguably the simplest gauge theory which we can define on a lattice, the Ising or so-called Z2 gauge theory. The classical version of this theory was put forward by Franz Wegener 50 years ago. And so we are studying the quantum version of this gauge theory in 2 dimensions. So we will be working on a square lattice where gauge fields will be living on links, and they will be spin 1/2 degrees of freedom. And the Z2 gauge theory is just a discrete cousin of electromagnetism. So the appropriate operators, which are Pauli operators, sigma z and sigma x, correspond to phases of U1 gauge field and the electric field. And the simplest gauge theory has this form. It has 2 terms which compete with each other. One of them is an analog of the magnetic term, where we have sum of products of sigma z's acting along plaquettes, and the appropriate coupling I will call J, the magnetic coupling. And then there is an electric term, which is just sigma x operator, and its coupling I will call H. And so this Hamiltonian is invariant under extensive number of local symmetries generated by this kind of operators, which are just product of sigma x's on stars. And this breaks the naive Hilbert space of the problem into a large number of superselection sectors, and we will pick one sector. So usually, if people want to study, pure gauge theory with no static charges, then we can get the so-called even gauge theory, where this generator is set to 1 at all sides. And so this theory has an interesting property, which was...
Sorry. We're still seeing like the gauge theory coupled to fermionic matter slide.
Sorry?
We are still seeing an older slide, I think.
I'm still talking about pure Z2 gauge theory. There is no fermion so far.
Okay.
Can you see my slides, or
your cover slide only?
Yeah, it's only the cover slide. It's the
Really?
second slide of the talk.
Cover slide still. So you cannot see me changing the
No, it's not changing now.
Oh man, I'm almost okay. Let me try to fix it. So yeah, this is funny. So let me try it again. And if so can you see me changing slides?
Yes, now it works.
Now we can, yeah.
I see. So what slides did you see? So
this one here.
This one and then nothing else?
Yeah, exactly.
Okay, so let me kind of come here. So you did not see this, so I think this is a bit embarrassing, but okay. So let me quickly say it again. So there is a magnetic term and the electric term, and they compete energetically. The magnetic term is product of sigma z along the plaquettes. the electric term is just sigma x. And I was saying that this Hamiltonian is invariant under this gauge transformation, which is just a product of sigma x's on the stars. And I was saying that if we do not want to have any static charges, just a pure gauge theory, we would fix these g's to ones everywhere, and this defines our theory. So I changed now the slide just to double check. Did you see that here it's good? So what actually Wagner already noticed, this is interesting property of this theory, is that as we change the dimensionless coupling in this theory, we go between two phases with a continuous phase transition in between. But these two phases can be characterized by a local order parameter. And so what Wagner realized back in '71 is that we can use non-local loop operators, which we call today Wagner-Wilson loops, to distinguish the two phases. And it was actually realized much later that even more robust way how to distinguish this is to study what is called topological order. So the deconfined phase is topologically ordered, which can be detected by measuring global properties such as degeneracy of ground state on torus. So this is a pure Z2 gauge theory, and then people started coupling it to matter, first to Ising matter in late 70s, but then around 2000 people started to ask a question: what happens if we take this gauge theory and couple it to fermions? So that first they considered a two-component case, and actually in recent years there was a lot of progress on that because people realized that we can do sign problem-free quantum Monte Carlo simulations. And they kind of, unveiled the quantum phase diagram, not only quantum, but also with temperature. So one of the interesting properties that the gauge theory here mediates attraction between fermions. So there is a transition between the strongly coupled BC regime and weakly coupled BCS regime with a confinement transition in between. So what we are studying is a single component case, which I'm showing on this slide. So instead of two components, we just consider one component fermions, which hop on between sides of the lattice. And these fermions, they carry Z2 charge. So for this reason, whenever we hop them, they need to carry with them the so-called electric string, where this sigma x gauge fields evaluate to -1. This comes from the Gauss law in this theory, as I will argue in a minute. So for this reason, there is this sigma z operator here. And so we can tune the chemical potential of these fermions with this term. And so now it's still a Z2 gauge theory. So this Hamiltonian plus the Wagner theory, but now the Gauss law is modified. And in addition to the star term, we also have the matter part, which is just a local fermionic parity. And if we want to work in the sector where there are only, Z2 charges carried by these fermions, the Gauss law starts to look like that. This is a discrete version of the Gauss law. So this is an analog of the divergence of electric term, and this is the matter, the density, which here plays a role by the fermionic parity. So this is a model which we study. And in addition to this redundancy, Z2 gauge redundancy, we also have a known as global symmetry here, which is just phase rotation of fermions by a constant phase. There is also time reversal symmetry here. So these are the global symmetries of the problem. Also, I would like to know that in contrast to this two-component case, this kind of problem, we do not know about any sign problem-free QMC. So it's a challenging task to understand the quantum phase diagram. Before showing you what we found about it, let me tell you a bit about motivation. So they are kind of twofold here. So one of them comes from cold atoms experiments, because recently with some ingenious proposals for Flaquet engineering in these papers were two experiments, one in Zurich and another in Munich, which build a basic building block of this problem, where we have two sites where matter can hop between, and a link where Z2 gauge field, dynamical Z2 gauge field lives. So now the hope is that we can scale up this building block, put a lot of them together, and form one-dimensional chains or even two-dimensional lattices. Another motivation comes from Kitaev physics. So it turns out that if we generalize the Kitaev model and replace Pauli matrices by gamma matrices, then we end up with a square lattice model where pairs of Majorana fermions live on sites, and this is exactly out of these pairs we can form a complex fermion. So this is our U1 spinless fermions coupled to Z2 gauge field. So before going on, let me ask, is it clear about what model we are studying and our motivations?
Yes, I think so.
Okay, excellent. So then let me tell you a bit what we found. So I will quickly describe four limiting cases where the problem becomes more tractable. Then I will briefly summarize how we can get actually rid of Z2 gauge redundancy and rewrite it in a nice form where everything is gauge invariant. And finally, I will show you some density matrix renormalization group results, which we found. So first about the limits, the simplest limit is that we tune the chemical potential to very negative values. This depletes the fermion density. So in the ground state, we have no fermions, and we are back to our even Z2 gauge theory, which I told you about before, with two phases and the Ising critical point in between. But we can do something related, but different. We can crank up the chemical potential. Then we fill the lattice with fermions, and since they are spinless, they just become non-dynamical, and every site has one fermion in this limit. This also reduces to a pure gauge theory, but now the Gauss law becomes strange because this star operator evaluates to -1. This is what is called the odd Z2 gauge theory, and its phase diagram is also known. And here we still have confined and deconfined phase, but now the critical point changes. It's like XY universality class, and also the nature of the phases become different. So for example, the confined phase necessarily becomes a solid, so it breaks translational symmetry. Another limit, which is also interesting, is just like, let's have fermions, let's consider, say, half filling, but let's make the tension in the strings which connect fermions equal to 0. It costs nothing to have these strings. Then what we have is just fermions hopping in the background Z2 magnetic flux. And the only thing we need to understand is in the ground state what kind of flux is preferred energetically. And here there are two regimes where you can understand it analytically. Either you make the hopping much larger than the magnetic coupling, and then you end up, due to the so-called leap theorem, to the ground state, which has pi flux, where every plaquette evaluates to -1. And this gives you a pair of Dirac cones. So you end up with a Dirac semi-metal half filling with a deconfined Z2 gauge fields. On the other hand, if you crank up, the magnetic coupling is expensive to flip plaquettes, and then we end up with a zero flux sector, and the band structure then looks just a cosine band. And you can study the transition between these two regimes, which was done recently in these papers. I think the most interesting regime or limit which we can think about is strong tension regime. So this is when H, this tension becomes very large. And then, what happens is that the strings want to be very short, and we start forming this kind of dimers out of every two fermions. And if we tune the chemical potential of order of this tension, then we'll populate in the ground state, make finite density of this. And in order to understand what we get in the ground state, we can do perturbation theory in the hopping of fermions and in the magnetic coupling on top of this, degenerate perturbation theory, where we have finite density of these dimers. These dimers cannot overlap because they are made out of these spinless fermions, and two spinless fermions cannot sit on top of each other. So when we do perturbation theory, the leading order comes from the magnetic term, it turns out. So if you have, especially if you have states or plaquettes fully filled with fermions, what this magnetic term will do, it will start to flip the strings, from the vertical direction to the horizontal, from horizontal to vertical one, and vice versa. And this effectively what it does, it mediates attraction, because you can lower the energy by making superpositions. So we have a short-range attraction between dimers due to this term, and this attraction is described by the famous kinetic term in the Roxer-Kivelson quantum dimer model. And so if we have a full filling of fermions, so every site is filled with fermions, then it's a fully filled quantum dimer model, and it's believed that the ground state is a solid, valence bond solid, with some kind of translational symmetry break-in, which has a columnar order. On the other hand, if you have partial filling of fermions, then this attraction will try to make a huge chunk, a big cluster out of all these fermions, and will get a cluster of this kind of dimers. So this is a leading node theory, but then you can also study higher order theory, and that's where the hopping starts to play a role, the hopping of fermions. And then you realize that these excitations in this degenerate perturbation theory has a peculiar properties, because the individual fermions, which are always connected to strings, they cannot hop, because then you kind of go away from your degenerate manifold in the perturbation theory, so they are completely immobile. But the dimers, for example, they are able to hop in second order, because you can first hop one fermion. This makes a long string, but then you can shorten it again, and then you have a dimer shifted towards left. So this is hopping in second order perturbation theory. But what is also interesting is that these dimers have restricted mobility, meaning that they can hop in their direction, like here, but you cannot hop them like here vertically, because this will also pull you out of the, or push you out of the degenerate manifold. So this hoppings in the vertical direction would not be perpendicular to their direction, are not allowed. So we actually worked out all the hoppings induced in the second order of perturbation theory of order d squared over 2h. And then what we studied, first we studied what happens to a single dimer in a such effective model. And what we found is that we found two bands. One of them is just a dispersive cosine band of order t squared over 2h, nothing too surprising. But also we found a completely flat band. And then later we realized that this flat band is made out of states which looks like that. It's some kind of superposition of dimers along plaquettes with these coefficients. And if you act with this Hamiltonian, this completely annihilates this. So there is an interference of hoppings, which makes this completely frozen. And out of these frozen states, this lower band is made. And so this is quite interesting, I think, because out of these frozen plaquettes, you can also make many-body states and study their properties. We also looked into small clusters. So I told you this magnetic coupling attracts things to dimers to make clusters, and these clusters become very heavy in this effective theory, and their hopping scales exponentially in their system size, because if you want to hop a cluster, you need to hop all the constituents individually, and this our exact diagonalization study is in agreement with this expectation. So let me now move away from just thinking about limits and tell you about some numerics. But first, let me briefly, I will be brief here, tell you that we can eliminate actually, the original model was written in terms of redundant degrees of freedom. And we need to impose a Gauss law to work in the physical Hilbert space. We can actually get rid of this redundancy and work with spin operators living on links, which are completely gauge invariant. And for that, actually, it's important to split the fermions into Majorana building blocks and then form some kind of bilinears. And if you use this kind of language of gauge invariant spin one half operators, you end up with a local Hamiltonian where spin 1/2 degrees of freedom are acting on links. And this is completely gauge invariant. There is no Gauss law anymore. And for the purpose of numerics, density matrix randomization group, this is the most economic way how to implement this model. This model is completely equivalent to the gauge theory which we started with. So let me show you some. First, what we are doing, we are studying our geometry is like infinite cylinder geometry. It's called IDMRG. So, and you know, the bottleneck is here this kind of circumference, which is finite and usually rather small. We often have Ly equals to 4. Sometimes we can go even like to Ly equals to 6 or 8, but this is our limitation with the MRG. So first thing what we looked into is, can we reproduce these limits, which I told you about, like even and odd Z2 gauge theory from the full model. And if you remember, both of these theories have a phase transition, so the Ising and XY phase transition, as we increase the dimensionless coupling. And so we look into the quantity which is called IDMRG or DMRG correlation lengths, and these peaks in this correlation lengths indicate that there is a continuous phase transition happening here. Especially you see that the peaks are growing as we increase the so-called bond dimension of our matrix product state. So then we also look. Okay, excellent. So we looked also into what happens in the presence of fermions. So here I show you some scans. So we set J and T equal to the same value, and then we scan in the chemical potential and the electric coupling, which drives the confinement. And so what we see is that in between this, there is this odd and even Z2 gauge theories. They have two phases. The deconfined phase has topological order, which we can extract from entanglement entropy. But the most interesting part is actually this partial fermion filling, where fermions are not fully, like partially fill the lattice. And I think the most, like hopefully the most robust and prediction which we did in that regime is at half filling, you know, where we have one fermion per two sides, when the magnetic term is completely switched off. So I told you that like if H is very large, right, then we have this dimer picture emerging in this theory. And I told you that these dimers can hop in this perturbation theory, but on top of that, they also actually, there is an induced next nearest neighbor repulsion between these dimers of the same order, d squared over H. And so what happens is that our numerics suggest that this repulsion stabilizes a mod state, so a translationally symmetry broken state, which has this form. And you know, the gap of this mod state scales according to our expectation from perturbation theory, and this is a strongly coupled regime of this half field case in the absence of the magnetic field. So now the interesting question is, if you have this state, how it will transition into the other state, which I told you happens at half filling, where H is very small. So the deconfined regime, which I argued is a Dirac semi-metal. So we have two phases, which one of them has deconfined fields, another is confined. One of them is translation invariant, another is breaking translation invariant spontaneously, how the transition happened. And so what we found, so we looked into different diagnostics, such once again as this correlation lengths, and also something which is called magnetic flux susceptibility, is just how the magnetic flux changes with the electric coupling. And what is exciting is that we see a single peak, or we see peaks at the same place, and this indicates that actually there is a single phase transition where both confinement happens and translational symmetry happens simultaneously. And this transition seems to be second order, so it's maybe continuous phase transition. At least, you know, on a cylinder which we studied, which is this Ly. This is data for Ly equals 4 cylinder. So, you know, it's an open question what happens in the thermodynamic limit, but it points, if this will survive, it appears that there may be an interesting quantum critical point. which happens here. So let me finish with Outlook. So I'd like to list some questions which actually I find interesting and to study. So one of the questions is actually what motivated me to look into this model in the very beginning is, in this Z2 gauge theory, gauge fields mediate attractions between particles. And so we expect that these single component fermions will undergo pairing. And this would be p-wave pairing necessarily. And so the question is, what is the nature of this pairing? So, and can we get a P plus IP superfluidity out in this problem, at least in some regime? Also, I think what is interesting is to study what happens at the edge, because there, this Z2 symmetry, which we are gauging, the fermionic parity, is actually survives as a global symmetry. So it would be interesting to understand its role at the edge, for the edge physics. Also, there is a question about thermalization, because when we are in this strongly confined regime and strong tension regime, everything becomes super slow, and it's good to understand how the gauge theory thermalizes, and if there are some exotic states in the bulk of the energy spectrum. And finally, this is something which I'm wondering about, if there are different ways to simulate these pretty challenging problems. I would really appreciate if somebody has ideas, maybe quantum Monte Carlo or two-dimensional tensor networks or digital simulation. So any new ideas how to attack this problem, I would be interested to discuss. So thank you very much.
Wonderful. Thank you very much, Sergey, for a nice talk. Questions for Sergey? Okay, maybe let me start asking you. I have a question on the DMRG simulations you're doing.
Mm-hmm.
So it seems like you're able to reach like very large bond dimensions, like also 300, 400. Mm-hmm. Does the entropy scale in this system?
Does the entropy scale in the system?
Yep.
So it depends. So the system is kind of complicated. So there are different phases. Mm-hmm. So the point is, if we have the gapped phases, then our DMRG is very good. So small bond dimension is enough, and so the scaling. But in the gapless regime, we have more problems, of course. So okay, let me see. So yeah, like if we are in the gapless regime, then the entropy grows. If we are in the gapped regime, we quickly can saturate the entanglement entropy. So.
Okay, but like as a function of the circumference of your cylinder.
Right. So yeah. So basically, yes. So for example, this is deep here. Mm-hmm. This is a deconfined regime where we have topological order. Mm-hmm. The entanglement entropy behaves like that. So it's proportional to Ly, and then there is this correction which is called topological entanglement entropy, this -1. Mm-hmm. So as you increase Ly, then the entanglement entropy is growing.
I see.
But what I'm saying is, like, if the system is gapless, then you will have increase in entanglement entropy as you increase the bond dimension, right? Somehow.
Right. I was just wondering if you see like corrections to area law.
So we see, for example, this topological correction, right? So this Ly times logarithm of 2 is exactly the area law, right? Because we are doing a cut like that. Mm-hmm. And so if we are going deep into this regime, the gauge field becomes deconfined, and we see this logarithm of 2, which is a correction to the which actually is diagnostics of the topological order in this regime. Yeah.
I see. Okay, thank you. I see Sri has a question.
Yeah. If you take your analysis and repeat it in higher dimensions, would you also expect fracton-like structures, let's say in 3+1 dimensions? And a related question that people have been trying to write down effective field theory for fractons. Do you know what kind of low energy effective field theory the fracton structure you found corresponds to?
Right, like the first part of the question is, I think it's pretty generic that if you take a, confining theory, then you get this kind of, I don't know if I want to overemphasize, I call it emergent fractonic phenomenology. So whenever you have, an expansive string attached to your elementary charge, and you start doing degenerate perturbation theory, which usually you do in a strongly coupled regime in lattice gauge theories, right? Then whenever you hop, you just go out of your degenerate manifold. So your elementary excitations become frozen. And if you start making stuff out of, two of them, they start to be mobile at second order perturbation theory. If you make bigger clusters, they will become mobile at high order perturbation theory. So I would say that it's pretty generic feature of confining gauge theories coupled to matter. And the other question was about what is the effective model for these fractons.
Yeah, in terms of I've seen people write down gauge fields and effective field theory in terms of
Right.
two-form gauge fields and so on. And so have you thought about that in this context?
Not yet. Yeah, somehow I thought about this in the context of elasticity of vortex crystals, but like not in this case, I did not think so. Okay, like you can think that this is an effective theory of fractons in a sense, like it's just like how these dimers hop, right? Somehow, but yeah, like I did not think about. You see, the point is that what you are mentioning is usually appears when you have translational symmetry breaking, which is spontaneously broken. You have phonons, and then you dualize that. That's but in this case we have a fixed lattice, right? So nothing kind of vibrates here. We have explicitly broken continuous symmetry by introducing the lattice. So I have so far no good ideas how to describe it beyond things like that. Yeah.
Okay, thanks.
Okay, wonderful. Thank you again, Sergey, for the nice talk.
Yeah,
I think
pleasure.
we should move on to the next one. So let's see, we have Piotr. Want to try to share your screen, Piotr?
I'll try to share the screen.
Okay. Wonderful. Okay, so our next speaker today will be Piotr Majewski from the Warsaw University of Technology. And he's going to tell us about solitonic excitations in heavy ion collisions and ultracold atomic gases. Piotr, the floor is yours.
Thank you, Alessandro. I would like to thank also Alex and Carlos for organizing this very inspiring interdisciplinary workshop that I learned a lot here. And it's a pity that we couldn't meet in person in Trento. So maybe next time. So I would like to tell you about our recent research on solitonic excitations in heavy ion collisions and ultracold atomic gases, and in collaboration with a couple of people that are listed here. I'm going to talk, in fact, about two things. So first, I will tell you about solitonic excitations in nuclear collisions that are, this research was inspired by solitonic excitations that one may create in ultra-cold atomic gases. And then I will tell you about stabilizing solitonic excitations by introducing locally spin imbalance. And that would lead to what we call Larkin-Ovchinnikov droplets or ferrons that have interesting properties and hopefully can be seen in ultra-cold atomic experiments. So let me start with nuclear physics. So just as a reminder, what we know about pairing correlations in atomic nuclei. So from odd-even mass staggering, we know more or less what is the strength of the pairing correlation in nuclei. We know that it scales with inverse square root of nucleon number. Unfortunately, this odd-even mass staggering is obscured by polarization effects. So there's always a quite significant uncertainty concerning the strength of the pairing gap for actual nucleus. There are other experimental data indicating that pairing correlations exist in nuclear physics. For example, high-spin experimental data, the famous example of backbending of moments of inertia that was observed already a long time ago, and it's attributed to the alignment of the nucleon pair, and it's a sensitive function of the pairing correlations. We know also that any theoretical description of large amplitude nuclear motion requires to include pairing correlations. So for example, if one would like to model nuclear fission at low energies, the inclusion of pairing correlations in this theoretical description is a must. So that's something that has to be introduced to obtain fission at all. So because otherwise the nucleus can hardly fission. Another question is whether we can probe the pairing phase, the pairing field phase of a nucleus. This actually has been tried for many years, and it started with the discovery of Josephson junction, and already in the 60s and 70s there were attempts to treat nuclear collisions as an example of a Josephson junction that is created for a very short time, and one can look at the enhancement of the neutron pair transfer due to the difference of the phases of the pairing fields. Unfortunately, to date, it looks like the experimental data that are available are not conclusive whether this enhancement really exists. There is very recent paper, it was very interesting actually, the very recent paper that treated colliding nuclei as AC Josephson junction that would lead to the oscillatory pair transfer. The interesting thing is that the authors looked not on the enhancement of the pair transfer, but on the spectrum of emitted gamma radiation, because the oscillatory motion of the neutron pair induces the oscillations of the protons, and this gives rise to the emission of photons. And what is surprising, that they found actually agreement with experiment. So that was so surprising that I even wrote a popular review of this effect, because that's seemed to be either a very strange coincidence or something really remarkable, because they analyzed only one type of reaction. So, and they got already very nice agreement with experiment. But then one can think about probing the phase of nuclear pairing field in a different way, which is motivated by experiments in ultra-cold atomic gases. So let me show you what in ultra-cold atomic gas one can study. So one can split the cloud of atomic gas and change the phase, the relative phase of one part of the cloud, and then merge these two parts of the cloud together. And then there will be a solitonic excitation that will appear in the region where these two clouds are merged. And this solitonic excitation is unstable. It will decay, and this decay pattern has been observed in experiment. In 2016, they identified several stages of this decay. So dark soliton decayed into phi soliton, then into vortex ring and vortex line. So we actually tried to reproduce the results. So we were using time-dependent DFT, density functional theory, and we actually were able to identify all these stages. So that gave us some confidence in the theoretical tools that we were using, and we asked ourselves whether the similar effect can be seen in nuclear system. So so this is what I would like to tell you about. But before I will show you results, so let me say a few words about the theoretical approach that we are using. So we are using time-dependent density functional extended to superfluid system, but extended to superfluid system in such a way that we use pairing field, which is local in space. So this locality of the pairing field requires that we have to introduce the energy cutoff. This energy cutoff is usually provided by the lattice on which we solve these equations, because otherwise, if we do not introduce this cutoff, the local pairing field introduces divergence. This divergence sits in the kinetic energy, which is divergent if we do not introduce the cutoff. So that was realized already more than 10 years ago. So with a prescription concerning relation between the effective coupling constant and the momentum cutoff, one can obtain the theory which gives finite results. So still this approach that formally looks like time-dependent Bogoliubov-Desgen equations, or like we say in nuclear physics, time-dependent Hartree-Fock-Bogoliubov equations. So still these equations are very demanding numerically, because there are a lot of amplitudes that one has to evolve in time. So the complexity of this problem scales with the lattice size. So we use supercomputers to solve these equations. So nowadays we can solve these equations for the lattices of the order of 100 cube, and we can evolve about 10,000 particles. So this is the approach that we are using. We are using this approach both for nuclear systems and for ultracold atomic gases. The difference sits only here in this H. There are contributions coming from functionals, and for nuclear physics we use, for example, Scherm functionals. For ultracold atomic gases, we have created functionals that work pretty well for unitary Fermi gas, both spin symmetric and spin imbalanced. So this is the approach that we are using. We have developed the package of codes that solve both time-dependent and stationary equations for arbitrary functionals. So this is the ongoing project. The main person developing these codes is Gabriel Blazłowski. Okay, so coming back to nuclear collisions, we can think about something similar, like for ultracold atomic gases. So we can ask ourselves what will be the result if we collide two nuclei having different phases of the pairing fields. Of course, we do not expect to have the same result as for ultra-cold atomic gases with all these stages of decay of this, all the stages of solitonic cascade that was observed in ultra-cold atomic gases. But we can ask, we may ask a different question. So what are the observable effect that can be seen in heavy ion reaction for nuclei, for superfluid nuclei? Clearly, in nuclear physics, we cannot control the phase, so all the results have to be averaged over various phase differences between colliding nuclei. But the observables that we would like to consider are the following. These are the kinetic energy distributions of the fragments. This is something that can be observed. We can also see we can also measure in nuclear physics capture cross section. So if we have two nuclei that merge, that we can ask the question, what is the impact of the pairing phase on the capture cross section. So before showing you the results, so let me first present what we can expect in this case. So if we have two nuclei that are colliding, having a different phases, that we can expect that there will be a junction that is created for a short time between these two colliding nuclei. It's just in analog of the junction between two superconductors that have two different phases of the pairing field. And we know from the Ginzburg-Landau approach that there will be energy stored in this junction that is proportional to the sine square of the phase difference divided by 2. So we may estimate what will be the effect from this expression. We may estimate what will be the effect of this phase difference on collision of two nuclei. If we substitute here typical values for nuclear systems, we obtain the energy difference between 0 phase difference and pi phase difference equal to 30 MeV. So this is a significant number in the context of nuclear physics. So this means that the effect can be seen in principle if this estimate is correct. So when we do the simulations for collision of two very heavy nuclei, like two plutoniums 240, so then these two nuclei after collision, so these are the snapshots from the simulations. So you can see, for example, on the right here, you can see the pairing field distribution. So in the case of pi difference, so you can see here the solitonic excitation that appear here, and then it stays here during the collision, and then stays until the nuclei separate. Then we can measure in our simulations what is the difference between the kinetic energies of the outgoing fragments after the collision as a function of the phase difference. And this is what you see here. So the kinetic energy of the fragments depends on the phase difference and depends on a particular way. If you fit these points with a curve, it turns out that it with a very good accuracy is a sine square of phase difference divided by 2. So this is exactly this dependence that we obtained from the Ginzburg-Landau theory. So in the case of medium nuclei, they can merge and stay together, and eventually they can fuse. And then the phase difference can be translated into additional energy that is needed for two nuclei to form a compound system. So then the difference between for zirconium-90 on zirconium-90 collision, we found that the difference of energy between collision of two nuclei with 0 phase difference and pi phase difference is of the order of 30 MeV. So this is more or less the value that one can obtain from this Ginzburg-Landau prescription. So even if we average this this quantity over many phase difference, over all the phase differences that can occur in collision of two nuclei, still we get the additional energy that is needed due to this phase degrees of freedom of the order of 10 MeV. So this is something that one can look at in experiment. 3 years ago, Guillaume Scams took all the experimental data on the capture cross section and analyze them to find what are the barrier fluctuations for collision of nuclei that are magic and non-magic. And he found that indeed there is a signature that there is additional energy, additional barrier needed for a superfluid nuclei to merge, although it's not, the effect is not this as strong as we predicted in this paper. It's actually order of magnitude weaker. So very recently we did a more realistic calculations with spin orbit term, because in these calculations here we did not include spin orbit term. So here we included spin. We took the realistic nuclear functional. We included spin orbit term, and our predictions actually dropped from this 30 MeV to about 6 MeV. So it looks like there is indeed a signature for a phase degree of freedom of the nuclear pairing field. So this certainly require more study and extraction of the capture cross section, which is unfortunately a little time consuming. So it will take some time for us to do such a systematic calculations of this effect across the nuclear chart. So this is one thing that I wanted to tell you about. And now I would like to skip to the second part of the talk. So now I would like to tell you about stabilizing nodal structures in spin imbalance atomic Fermi gas by inducing locally spin imbalance. So we know that having a stable nodal structure for spin imbalanced Fermi gas was predicted by Full-Deferel, Larkinov-Chinnikov. Unfortunately, although there are some predictions concerning existence of the Larkinov-Chinnikov configuration for a certain spin imbalance range in ultra-cold atomic gas, it's very difficult experimentally. It's very difficult experimentally to detect such a phase due to the inhomogeneity of the trap. There is some hope that in the nearest future, due to the ability of producing flat traps, this existence of this Larkinov-Chinnikov phase will eventually be resolved. But one can actually approach this problem from a different perspective, and one can ask the question whether we can produce the Larkin-Ovchinnikov droplet by as an excited configuration in a spin symmetric system by introducing locally spin imbalance. So imagine that we apply locally in the system the spin selective potential that will locally break Cooper pairs. And then what will happen is that we produce the nodal structure of the pairing field that is stabilized by the local spin imbalance in the form of the spherical nodal structure. So that we actually perform the numerical simulations that you can see here. What you see here, we apply the potential that locally breaks the Cooper pair, introducing the spin imbalance locally, and then after switching off the potential, this stable Larkin-Ovchinnikov droplet stays there. It does not decay because it is stabilized by the spin polarization that occupies the nodal lines of the pairing field.
Piotr, you have 3 minutes.
Okay. So this is an interesting feature that we actually investigated further. We found that this structure is surprisingly stable. For example, we can, as you can see here, we can collide these structures, and they still they do not decay. They can merge. They can collide. They still keep this nodal structure. In our approach, this object is absolutely stable. So it does not. There is no signature of its decay. So it has a very peculiar structure of Andreev states. So these Andreev states are responsible for the stability of the structure because they accumulate the polarization that occupies the nodal line. So the spectrum of Andreev states of such a spherical ferron can be schematically seen here. So it is practically degenerate. So there is a gap here. So these are sub-gap states, and the occupation of these states produces the non-zero spin polarization. So it has a very interesting properties. We can treat this object, which we call ferron, as a composite particle. We can calculate its effective mass. Its effective mass actually is composed of two terms. One is simply the excess of spin-up particles that reside in the nodal line, but the second term is due to hydrodynamic contribution, and it turns out that for sufficiently large ferron, this term dominates over this one. This is interesting because this term scale with the surface, because the spin excess particle sits at the surface, whereas this term scales with the volume. Still, for the large object, this term dominates, which can be seen on this plot. And the last slide, which I would like to show, is that this object that I'm telling you about has also a peculiar property, that there is a certain limiting velocity with which this object can move through the superfluid. Namely, if we are dragging the object, trying to accelerate the object and to to make it move through the superfluid with a certain velocity, we can do it only to a certain extent. At some velocity, if we try to accelerate it beyond this velocity, we cannot succeed. It stays with this. It stays with this limiting. It stays with this limiting velocity, and this limiting velocity depends on the size of this object. So this is an interesting property that is again related to the structure of Andreev states inside this impurity, namely the Andreev state of the object which is moving through the superfluid. The Andreev, this band of degenerate Andreev state is splitted, and the splitting is proportional to the difference of chemical potentials between spin up and spin down, the local chemical potential between spin up and spin down particles, and at the critical velocity, the splitting is such that the lowest Andreev state hits zero energy, and this is the point when the ferron becomes unstable. So this is the origin of this critical velocity that we see here. It has an interesting consequence concerning the interaction between this object and quantum vortex. So the quantum vortex produces the superflow, and if we try to generate ferron in the vicinity of the vortex core, we will not succeed. And this is what is seen here. These are the snapshots from the simulations. This is the core of the vortex. And then we try to produce the ferron in the vicinity of the vortex. And as you can see, it decays. And this is due to this limiting velocity. Simply, if we are too close to the vortex core, the ferron becomes unstable. So we are looking forward to some experiments that would help us to verify whether this object really can be produced in experiment and whether they can be studied. So we are hoping to have some input from our colleagues from Florence concerning this particular object. So this is an example of Larkinov-Chinnikov droplet that is an excited configuration of the spin symmetric system. So this is the last slide, and I would like to show you the other fields that we are investigating with this approach that I was telling you about. So with this time-dependent density functional theory extended to superfluid systems. So thank you very much.
Wonderful. Thank you very much, Piotr. Okay, we have time for a few questions.
I have a very practical question. You mentioned earlier implementing the spin orbit into your code. Was this done perturbatively or self-consistently?
No, self-consistently.
Okay. And it was a sizable, like more than 20% effect?
Yes, it was more than 20% effect. Yes.
Okay.
So that's true.
Okay, thank you.
Okay, has he answered the question?
Yes. So I found this discussion of the collision of nuclei in the first part of your talk very interesting, and I would like to understand this a little bit better. So what are the typical energies the nuclei have in this collision, and what would you have to do to measure this effect? So how would you do this experimentally?
Okay, so the collision energies are just above the Coulomb barrier. So, for example, here, as you can see, for the collision of this medium nuclei, it's of the order of 200 MeV. So this is more or less the height of the Coulomb barrier. Now, in this case, the quantity that would be important is the capture cross section, because in this case, one expects that one expects that these two nuclei is sufficiently high energy that they merge. So one should look at the capture cross-section as a function of energy. The best would be to look for a chain of isotopes going from a magic system to non-magic system to see the effect of superfluidity. So this is the first thing that we would like to look at. Unfortunately, the capture cross-section requires to do many simulations with non-zero impact parameter, and this is very time-consuming. So this is the reason why we didn't do it yet. Another thing for heavy nuclei, of course, they do not merge, but then we can look at the total kinetic energies after separation, because as we found, this phase degrees of freedom, the degree of freedom gives rise to additional kinetic energy, because the mechanism is the following. So the two nuclei collide, and then part of the energy is stored in the solitonic excitations, and then it's released when the nuclei separate, and this stored energy gives rise to the additional kinetic energy of the fragments. So this is something that one can look at. So these two observables are the most promising ones in my opinion.
So I mean, you want, what is the reference line for this additional energy, right? If you have the nucleons colliding, initially they're very far apart, and then so you know this energy from the accelerator, and then I would assume that there is no energy stored already from this effect, and then they approach each other, and then maybe some energy gets transferred. But
one has to compare the kinetic energies between a superfluid case and the normal case. So one has to take like collision of two lead-208 and compare it with a collision of let's say other isotopes of lead that are non-magic and produce some pairing correlations, and only by this comparison of the kinetic energies and comparing the expected kinetic energy increase in the superfluid system as produced by this theoretical approach, one can find some signatures that this effect is present. Well, I would, however, think that the capture cross-section is better to look at, because in the case of these collisions, when you collide these two nuclei, so they also get excited internally, so they will most likely emit neutrons. So to measure the kinetic energies of the fragments may not be so easy, because they already will emit neutrons right after collisions, for example. So I think the better is to look at the capture cross-section of medium nuclei.
Okay, thank you.
Okay, wonderful. Thank you again, Piotr, for the great talk.
Thank you.
And I also want to thank all the speakers of today for the amazing talks, and all of you for contributing to the discussion. So we have half an hour of discussion session right now. Maybe before starting that one, Sri had a question for Thomas. If you want to ask the question to Thomas.
Yeah, can you hear me?
Yeah.
Yes.
So the question I had was really whether there is any phenomenological effect for the nuclei that is similar to quantum Hall effect? Is there anything that can be measured that is similar to the quantum Hall effect? That's what I wanted to ask.
I'm not sure. So what typically is measured are excitation spectra and gamma ray transition probabilities between those states. Yeah. And so in that sense, there are not any transport properties in contrast to the quantum Hall effect or so. Okay,
I see. I mean, that would be very interesting to think about if there was something like that. Okay. Is there, are there any kind of edge physics that could come out of this?
I don't think I have only started to think about this here based on this workshop, but I don't think so, because here in this case the sphere is really it's not mapping a plane onto a sphere and discarding edge physics, but rather there is no edge. In my leading order answer would be there is no edge physics because this is just the space we are dealing with.
Okay. All right. Thanks.
Francesco, who's going to lead the discussion session today.
Yes.
Hi, Francesco.
Hello. So today we heard a number of interesting talks that somehow I think share two important features. The first one is the fact that essentially you can push formal analogies very far, and say, I mean, this all comes down from if you think from the very old concept of quasi-particles that was in some sense the first, well, I mean, at the times was an attempt to describe in some way a phenomena using somehow a formal analogy, but with physical implications that we all know. I mean, that has been so. This has gone very far. This has gone very far, and I think that this is sort of a kind of common feature that we find in this business these days. I mean, there is a lot to learn just from, in some way, looking at equations and establishing these formal analogies. And the second thing is that there is a sort of, and it's also quite obvious in some sense, but let me just bring it up. There is a lot of room for simulation, meant in terms of, say, trying to find really new ways of performing, or also for solving theories. I mean, yesterday I said something about quantum computing and algorithms. I mean, I think that quantum computation these days is still in such an early stage that essentially still an experiment, okay? It's a sort of very organized experiment, and I think as Zora, unfortunately wasn't able to hear what she said, but at the time, but I think that we're still not at a level in which you cannot separate somehow the experiment from the computation. At least when you really go and try to do things, not just when you write down things on paper. So all of this is very important, I think, because this suggests ways, alternate ways in which one could go in order to understand how to exploit quantum physics in order to solve problems in general. Okay, so that's still very open, and I think that it's very useful to have this kind of exchange of ideas. So I don't know if anyone wants to put down some comments, either for general terms or specifically for any one of the speakers.
So I have a question for Zore. Sorry, I'm being a little more specific than general. Zore, are you around?
Yes, I am here. Go ahead.
Yeah, so this relates to your talk from the day before yesterday.
Mm-hmm.
And you were commenting about Chern-Simons theories and how you were able to map it to another system with Jordan-Wigner transformation, for example. And so what I was
it's a generalized Jordan-Wigner transform in SA. It's a generalization of the transform to 2 + 1 dimension, but yes.
Yeah. So what I am curious about is that whether something similar can be applied to a mixed Chern-Simons theory and so on. Do you have any suggestions on thinking about that, or?
So you mean, what do you mean by mixed exactly?
So I don't know if you were there in my talk. It was really early today, but basically.
Yes, I was there. So you were talking about 2 types of gauge fields. Is that what you mean?
Yes. And so I had a mixed Chern-Simons term between the 2 types of gauge field. Yeah. So
as long as they are coupled to fermions, in the way that I showed in the Lagrangian, yes, this is possible. I think you have to figure out what the Gauss's law is for the mixed theory. So in just one single gauge length with the fermions, there is a simple Gauss's law that we take advantage of to kind of simplify theory in this form of fermionic or spin representation. That's really one of the tricks. So I guess, do you have 2 types of Gauss's law or 3 types of Gauss's law because it's a mixed theory? How does it work?
Yeah, so that is something I haven't thought about yet, but I'm guessing there should be 2 types of Gauss's law.
Mm-hmm.
And the bigger problem for us is that, we want to integrate out one of the gauge fields, and that creates a sign problem for us. And so the hope is that, if you have a system like you were writing down for your, Chern-Simons theory, if you have a system like that, maybe there is no sign problem. I'm not sure if we can map the mixed Chern-Simons term to a term that you were writing down. So
yeah, so I would say, I think that the first step is to write down the Hamiltonian, so the sort of a fixed time, continuous time Hamiltonian out of the Lagrangian. The second step to figure out what the Gauss's law are, and then try to eliminate degrees of freedom using that on the 2-dimensional lattice. And the third, figure out what are the transformations of the field that can actually simplify the Hamiltonian farther. And in this case, you might actually need to impose certain commutation relations. So in the case that I presented, there was a theta parameter in the Lagrangian, and only for certain values of this theta parameter, you actually recover these hardcore boson commutation relations, which are spin representations of the theory. But you can have other generic commutation relations for different values of theta. That would be another interesting theory, another dual, which is not a spin representation. So that would be kind of the third step. I can send you a note on how this is done, at least for the theory that I looked at. And this is well known. This is what Fredkin, I think, did a couple of decades ago. Yeah, so if you can then reach a Hamiltonian formulation, they can be mapped to to a simulator. I think yes, then that would be interesting. That means that you can deal with this problem without the sign problem that you're mentioning.
Right. Yeah. Okay. All right. Thanks. That was great.
No problem.
Okay. Thank you. Other comments?
Comment, Larry, connected to what you, Francesco, were saying about effective degrees of freedom and quantum computation. And in a way, like the existence of low energy theories that are like shared among different systems, say like unitary Fermi gas and neutron matter, for instance, or like universality. It's kind of like at the heart of the expectation that we will be able to like simulate quantum systems using different quantum systems, right? And like, I think one of the main advantages that we as nuclear physicists and also like in condensed matter, it's also very similar. We have, and we can exploit in quantum simulation, is the fact that like we know how to manipulate effective theories. And that has an extremely big potential in allow us to like extend the reach of the quantum platforms that are available at the moment, because you can essentially look at quantum simulations as performing a low energy effective theory on a different machine and try to mimic the behavior of a second one. Right. So I think there is a lot of room for using ideas from EFTs, and especially like order by order expansions, to both like formulate simulations, but also like to control imperfections in machines. In a sense that like effective theories tells us what features of a simulations are appropriate for the physical model we are trying to describe, and it's very likely that they will also allow us to understand what contribution of errors are coming in what we're seeing from experiments, right? So it's very possible that like one can use EFTs to devise ways of detecting errors or possibly even correcting them at a perturbative level. So I think there is a lot of interesting things that one can do in that direction.
In this sense, I think that there is an issue which is also interesting to follow. It's related to what you said in the end. I mean, what are the limitations of the applicabilities of this parallel that one is constructing? Because effective theories might hide somewhere, let's say, problems that at a certain point jump out. I mean, I always remind the problem of somehow reconstructing the physics of nuclear matter at relatively high density, not low density. Low density is somehow an easy problem. But starting from what you know from nuclear, the problem is that you have no experiment to check your results against, in some sense. I mean, when you go to the core of a neutron star, you cannot go there and dig. Okay, so you really have only to rely on the scheme to some extent if you want to do some serious theory. And there, it's very important to find condensed matter systems that allow you to study this. For instance, there's something good I am in this case. Just look at helium. We know everything about liquid helium. I mean, it's something that we've been knowing for 40 years, probably 50, 60, I don't know. I mean, it's a very old business, okay? Still, it's interesting because we know everything from the physics of droplets to the physics of droplets with impurities to the physics of mesoscopic systems to the physics of the bulk, okay? And that's a very interesting simulator for a strongly interacting system. You have bosons, you have fermions, mixtures of bosons and fermions. You can play with it, and you can play with it pretending you don't know. I mean, that's the important thing. I mean, the simulators should help you to develop theories in which you pretend you don't know what's going on. You try to reconstruct it. So in that sense, what I heard today is very interesting because somehow well, first, as the case of the quantum Moore effect. I mean, the quantum Moore effect is not new. Still, somehow you could imagine that you exploit devices essentially which can make measurements in order to you take the opposite attitude. I mean, you have a mean field theory, okay, that somehow is able to reproduce the quantum Moore effect from a different perspective. And now I'm thinking, why don't you use a device, a solid state device that essentially displays quantum Moore effect to try to solve relativistic mean field theories? You know, I mean, I think that this is, and is this possible? How? What is the limit? Is there enough flexibility or not? I mean, I think these are interesting questions that we can ask.
Yeah, exactly. And I think also, like,
yeah. Can I add a couple of cents to the discussion, maybe?
Sure.
Okay, maybe I should put my video here. I don't know. Okay, so I you know, of course, effective low energy theories are generally quite useful when it's possible to obtain them, right? Typically, you have to worry about precisely a very nice separation of energy scales to make sure that you're capturing all the degrees of freedom for that, right? One classical example in which this low energy theories fail miserably. It's one example in which you can see in cold atoms, for instance, which is that the BCS-BC problem. If you just do a pure BCS theory, it's, oh, I'm going to just look at the low energy fermions, and you forget about degrees of freedom that arise from the formation of two-body bound states, your effective field theory is completely wrong. It works well on weak coupling, but not at strong interaction, and definitely not at unitarity, right? So the idea of developing those theories, I mean, you have to be very careful to see if you're not missing any of the important energy scales, which sometimes are very far off from the natural energy scale that you're thinking about, right? So if you think about highly degenerate systems, the Fermi energy for superfluidity, yeah, that's the natural energy scale. But if the interactions become too strong, too attractive, another energy scale comes up that you cannot ignore. And that your effective theory is completely different, right? It has to include those additional degrees of freedom. And to put in a more broad perspective, it is always nice, if whenever it's possible, this is very difficult, but if there are some really serious constraints that you can do, like sum rules of whatever properties that you're looking at, those can produce very serious bounds and limit, right, where those effective theories can work. And I bring it from condensed matter perspective. There was a huge debate many years ago about the F-sum rule in high TC superconductors, right? We know and love the F-sum rule. It's been around forever. It's just quantum mechanics, which basically states that if you integrate the optical conductivity over all frequencies, right, you're essentially measuring the average kinetic energy of the system. And so people were developing theories for this very hot problem, right? It was clearly agreed upon that if you could explain high TC, it was a sure Nobel Prize awarding thing. But yet none of the theories that were around, could handle very well that sum rule. They all violated somehow, and that was some kind of very important constraint. I think sum rules is one example, but if one can come up with very serious constraints, yes, we can talk about very interesting physics, which violates a lot of basics. We shouldn't be really seeing it, right? And if we see it, there's some other explanation, not the one that's provided by those effective theories.
These are very good.
Because if they violate something fundamental, then it shouldn't be applicable. So I just bring 2 cents to the table based on my experience in condensed matter physics. Sometimes a theory that explains something, right, violates something so fundamental that you have to be careful in seeing why it explains at all. And that's just the example from the high TC that I'm trying to bring up.
This typically pops out somewhere. I mean, sooner or later you hit some problem in general, and that helps to establish the limits in some sense of.
Yeah, and experiments may help us, right, guiding the thinking. So before you said, oh my gosh, people start realizing, oh it violates the sum rule. Everybody violates. So nobody has a theory, even though these experiments agree. They agree with that experiment. They agree with that experiment. There's a fundamental theorem that all those theories were violating, even though many people claim that they explain that experiment, they explain the other experiment, and then it comes to a crucial point. They all fail, and they're all effective theories.
Oh, sorry. Zora manifested herself, so I guess that she has to say something, right? No.
No, not necessarily. Sorry. I'm just listening, and maybe I comment at some point if something arises.
I thought you were asking for the floor.
If I may make a comment on what Carlos said. So I agree with everything you said, but the whole idea of an effective theory is that you separate known physics from unknown physics, right? Now, if you have known physics and you use the wrong degrees of freedom, well, that's on you, right?
Yeah.
No, sure. What I'm trying to say is that effective. I love effective theories. I think they're wonderful tools. But the only thing that I'm trying to bring up as a 2 cents comment is that sometimes we get very attached to our own effective theories, and we push it beyond its limit of applicability. So we should always be cognizant that it's a wonderful concept. It's a great thing. We all use it. It should be encouraged because you're trying to simplify the problems which are otherwise tractable. But we should think of it as a useful tool to apply to the properties, at least, that we can. We cannot just make, sort of say, oh, this should be the ultimate. No, we can explain a few things here and there, but the ultimate thing could involve other things. And that works well when these energy scale separations are possible. But there are some problems which this cannot be done. So you have to include maybe you have to create a hierarchy of effective theories, including the right degrees of freedom, not just the obvious ones.
And then match those, right? Yeah.
And match those, yeah. So I'm not criticizing that. Actually, I think it's a great thing, but that sometimes requires the feedback from experiments. That's what I'm trying to say. Putting the experiments in the mix, they give us feedback and say, gee, there's additional degrees of freedom that the experiments are throwing at us that it's really necessary to include. And that's why we do physics, right? I mean, without experiments, what is physics? We need the experiments, the feedback. That's all I'm trying to bring in.
More comments or thoughts?
Maybe on a different note, thinking about the theme of this workshop being condensed matter and nuclear physics meeting in terms of finding analogies in physics problems in different disciplines that we can find and hopefully understand the problem of interest in our discipline based on those analogies. I think there is another avenue that these two fields can meet, and they have, which is in terms of methods, right? And particularly computational methods. I think dealing with all sorts of sign problems, for example, and understanding kind of the similarities and differences between different types of sign problems and what is the kind of underlying physics that is causing it would be interesting. And I think people are thinking about it, but also kind of sharing ideas about how to develop various methods to go about these. In lattice gauge theory, people are thinking about sign problem all the time. And I know that there are, in fact, communications and conferences between the two communities about this particular problem and computational avenues for it. So I think would be worth also mentioning this just as a passing here. that I think sharing the methods and ideas for computations and simulation is important too.
It's good that there are communities that actually practice this commonly. I mean, well, there are a few of us here that belong to the, let me call it in very general terms, the quantum Monte Carlo community, and say it's absolutely common to have gatherings of people who do completely different things. I mean, completely different physics. They actually can talk to each other because of the methods. I mean, that is very useful because in general, the problem that you have when you try to solve a certain issue maybe is there somewhere else, but people never thought about it. Or I mean, this is very common. I mean, I had several experiences in those terms, and I think it's a very good example. Yes.
Yes, indeed. But I think also, like in terms of understanding this kind of pathologies with the type of data we're looking at for different physical systems, like on lattice QCD side, nuclear correlation functions have this infamous signal to noise problem, and it comes kind of from the statistics of looking at the statistics of these objects. They are very non-Gaussian, right? And they have like heavy tails, and understanding like where these heavy tails come from, right? What's the underlying QCD physics that is causing this? And then maybe looking at the other fields like in condensed matter and see whether there are systems that are seeing similar pathologies and what is the underlying physics for that. And kind of building on that analogy, maybe to understand better what we're dealing with in our lattice calculations, right?
Thanks, Ole. More comments? We have still a few minutes if you want.
So I have a question regarding the sign problem comment. Are there examples where, some simple system where sign problems have been addressed by, real-time simulations, like some kind of quantum computing analysis has addressed the sign problem? Or which sign problems would you expect to get handled in the near term? So yeah.
Is that for me?
Anyone.
Yeah, I would say practically for small systems, real-time dynamics has been done. So this is known to have a sign problem, but I think we should be careful because like sign problem is a problem with the method, right? It's Monte Carlo sampling method that show the sign problem, right? This cancellation problem or this complex weight for sampling. And so if you completely change your method to, for example, Hamiltonian formulation and do it in a different way, then can we still use kind of the same term that we kind of solve the sign problem? Because we didn't solve the sign problem in Monte Carlo calculations, right? With the given method within that framework.
These days, I mean, there are around plenty of examples of methods that essentially, rather than working in coordinate space, say, when you try to call Monte Carlo, you have whatever your coordinates are, and you sample on those. You work in Fock space instead. So if you work in Fock space and you have a system that is sufficiently small, it's likely that you're not seeing the sign problem because essentially you're already working in a space that is limited. There is another problem that you have that you need to consider essentially a field of space which is sufficiently large. But like you are able to perform exact diagonalizations, let's say, that are sufficiently exact in many cases. For small systems, you can probably find solutions of this kind that sort of hide away the problem. Okay. The essence of the sign problem is an asymmetry that needs to be broken. The fact that essentially you are trying, in general, when you deal with fermionic systems or excited states, you have to deal with a wave function that essentially has as pockets, I mean, as locations in which it's positive and in which it's negative. Typically, these are symmetric. If, for instance, if you take the fermionic ground state, these are symmetric. I mean, that it's a theorem. But the Hamiltonian doesn't know anything about it. And that is the problem. I mean, if you rely on a method that says, okay, this is the Hamiltonian, give me the solution. The Hamiltonian doesn't know about the symmetry of the system. So unless you're really able to select that part of the Hilbert space that contains your solution, which is typically part of the solution. So, I mean, it's a sort of self-consistent problem. There's no way out. I mean, that's the problem. Unless you're able to break the symmetry in some way. I mean, so you find a way, you find, for instance, some propagator that makes or is able to understand that the solution has to be broken into parts, where it's a positive and a negative part. But without breaking that symmetry, the Hamiltonian doesn't know anything about it. And so if you want
so what you mean, Francesco, I guess, is that knowing about that symmetry requires block diagonalizing a large Hamiltonian, which is computationally expensive.
Yes,
right. So the Hamiltonian contains the symmetry, but like breaking it down to blocks and reducing the size of Hilbert space within those symmetry sectors is computationally hard.
Yes, it looks like it's exponentially hard. I mean,
yes, right.
The idea that quantum computing can help is exactly there. I mean, if there is something useful in quantum computing, might be that that problem might be reduced from exponential to something less than exponential, maybe badly polynomial, but that would be already a victory.
Can I add maybe a couple of cents on this thing also? I used to joke, I mean, like the problem that you guys are posing in the past, that in physics, we should start having somehow get a community or a conference or something like that that would propose, right, what the mathematicians do typically over the years. Is everybody have to have a broad discussion, or at least a subgroup or area, and you identify what is the most important problem that needs to be solved, okay? And that you make it a decadal problem, or a centennial problem, or a millennial problem. It may take 1,000 years to solve. But the question is, we seem to be so spread around in doing all kinds of different things. And there are some problems, like, for example, the one that was discussed now, which are very, very, very important, right? And at the end of the day, we spend very little time trying to solve them because we know it's very difficult, right? Nobody wants to put a career to try to solve this problem because you know the chances of succeeding are exponentially small, right? It's exponentially hard problem to solve, and the chances of succeeding are exponentially small. But nevertheless, you know, keeping the spirit of a general posing question, I think it would be nice, and I hope someday I will participate in a conference or even organize one, in which the goal is to bring people together on a field at least and say, look, what is the most important problem? Let's say even theoretically, but we need the experiments too, right? Physics is an experimental science. But what's the most important problem that we all need to be working on to try to solve? We can do the other things to survive, right? Because everybody has to survive. But then we have to identify what is the millennial problem? What is the centennial problem? What is the decadal problem? And then we do this maybe on the side, because most of the funding agencies will not really support those things by considering it extremely risky. Just 2 cents to bring up to the you know, the point of this issue, which is an exponentially difficult problem to solve.
A good proposal for an ECT workshop, maybe.